Welcome students. In our previous class, we have discussed about what is semiconductor and band structure of solid, and according to band structure, we separated the conductor, insulator and semiconductor. Okay. And we have told that semiconductor, pure semiconductor like silicon or germanium, they have less number of conductivity, very less conductivity. So due to this conductivity we cannot use directly the semiconductor, but we can control its conductivity by the process of doping. And doping means the mixing of impurity, pentavalent or trivalent. Okay. So depending on the impurities, we divided the semiconductor into two types: p type semiconductor and n type semiconductor. And p type semiconductor mainly basically, if we uh, doped the impurity of trivalent atom like boron or something, then this is called trivalent, p type semiconductor. And for p type semiconductor, majority carrier is 4, remember is. And for n type semiconductor, the majority carrier is electron, and we introduced here the trivalent molecules, pentavalent. And there is a law of mass action, that number of electron and number of hole multiplication of this is always constant, which is equals to ni square. Okay. So today we are going to show a very interesting device called PN junction diode, which is very important device for our modern technology and modern life. Okay. And our life are completely depends on diode, like light emitting diode, LED, photodiode, which is used in solar cell. Okay. So we will discuss here. So first, PN junction. PN junction means when a pure semiconductor material such as silicon or germanium is doped with impurity in such a way that one side has large number of acceptor impurity, means p type, and another side has large number of donor impurity called n type. This device is called PN. Means one p type and n type semiconductor just connected like this. Okay. In case of, you can see this picture, there is p type semiconductor. Basically we take a pure semiconductor and then doped, one side we doped p type and another side we doped n type. Means one type, for p type we doped trivalent molecules, trivalent atoms, and another side we doped pentavalent atoms. Okay. Then there is a in junction region there is a process called diffusion occur. So, and due to diffusion, a barrier or region we get. This region is called depletion region. How this region occur, I will explain. Okay. When p type and n type connected, means when the reach side by side, so as p type has large number of hole and n type has large number of electron, so there is an diffusion occur. Okay. So due to diffusion, the hole of p side start diffusing towards the n side, and electron of n side started diffusing towards p side. Okay. That's why a region occur where no hole and electron, we cannot find any hole and electron in the middle region. Okay. Because hole and electron are cancels each other and they becomes neutral. Then we get only the immobile ions, means non-movable ions. Okay. Means for p type, we know, suppose we doped with boron. Boron means boron has 3 electron and 1 hole, and 1 hole is accepted an electron. That's why now boron has 4 electron, means boron becomes B minus. These B minus ions are here. Okay. By accepting electrons. Okay. This is 1 B minus, this is 1 B minus, B minus, B minus, B minus. These are B minus ion, means boron minus. Okay. So In p side we get the negative ions, immobile ions. These are called immobile ions. Immobile means non-movable. Okay. In n region we get like that positive ions, means suppose we doped arsenic. Arsenic has 5 electrons at its outer band. Then one electron is has gone towards the whole side, means p side. That's why the arsenic now becomes As plus. Okay, these are the As plus ions. Okay, and that's why this region there is no mobile charge carrier, means movable charge carriers. Okay. But we have also some electron in p side, very less number of electron, because we know that n into p number of electron and number of proton, electron density and proton is equals to ni square. Okay, so we get some very less number of electron also in p region and less number of hole in n region also. Okay. So this is the construction of diode. So in depletion region, so but you can see here that due to diffusion, whole number of electron means the in p region there is a large number of hole, and all the hole, and in n region all the electron may diffused and their whole region may be neutral becomes. But this not happens, because you can see due to this immobile charge carrier the electric field produced from positive to negative. Okay. This electric field repels the hole to diffuse towards electron n side, and also this electric field repel the electrons to go towards the p side. That's why we get a depletion region, and depletion width of the depletion region depends on the how many electric field here occurs and the width of the depletion region and also the doping concentration. Okay, so the now what happens, and the now diode is made. Okay, and it has two terminal, one terminal coming from the p side and another terminal coming from n side. Okay. So in middle region there is also a potential difference because of immobile charge carrier. Width of the depletion layer depends on proportional, inversely proportional doping concentration and directly proportional to the temperature. Okay. So there is a potential barrier, means for p side we have negative immobile ions, and in p n side we have positive immobile ions. That's why the potential barrier occurs, and if I choose the zero potential at the junction, then we get the potential barrier like that. Okay, and the barrier width is known as the potential difference between p side and n side. Okay, and this is called barrier height or barrier potential. And for germanium the barrier potential near about 0.3 volt, and for silicon barrier potential near about 0.7 volt. So as we have a barrier potential difference, so if we connect a bulb here, that means then bulb will glow or not? It will not glow, because there is a junction, metal semiconductor junction in both side of p type semiconductor and n type semiconductor, and at this junction the reverse potential barrier occur here and here, and the combination of this potential and this reverse potential becomes zero. That's why we cannot get any potential difference, or we cannot measure this potential difference by any voltmeter, or we cannot glow any bulb by using this diode. Okay. So another term, diffusion and drip current. So you can see here is a diffusion occur from for hole diffuse from p side to n side and electron diffuse from n side to p side. This current, due to the diffusion of electron and hole, we get there is a current. This current is called diffusion current. And there is also a drift current, because for immobile charge carrier you can see there is number of electron or hole also, electron in p side, some electron in p side and some hole in n side, and these electron or hole, the electric field support to flow these holes and electrons, and that's why due to this electric field the minority carriers electron moves very with high speed from p side to n side, and hole also move from n side to p side. This current is called drift current, and in equilibrium the drift current is equal to diffusion current. Okay, you can see, and as a electron hole pair, because of thermal collision, are continuously created in depletion region. This regulation flow of electron towards n side of n side and the hole towards the p side. This make a current from n side to p side. This current is called drift current. So the electron hole pair also here created, and continuously creation and destruction, continuous process is going on. That's why the electron hole pair, always electron going from n side to p side, sorry, hole going from n side to p side and electron going from p side to n side, and this current is called drift current. Okay, so in summary, we have a p-n junction and there is a depletion region, and in depletion region, due to the immobile charge carrier, we get a potential barrier and just this, and we have two terminal of p-n junction, and we cannot use always the p-n junction diode like this structure, so we use a symbol. p-n junction symbol is like that. Okay, just like that. Now this is p side and this is n side. Okay, p-n junction. So now biasing means now we have to use this p-n diode for our different purpose. That's why called biasing. There is a two type of biasing. One is called forward biasing, another is reverse biasing. Forward biasing means if we connect with a voltage source, then if we and positive side of voltage source connected with positive side of diode and negative side of voltage source connect with the n side of diode, you can use this structure also like that. Okay, this is p side, this is n side, and we connected positive terminal of battery with the p side of diode and negative terminal of battery connected with n side of diode. Okay, so what will happen, you can see this is our diode, this is p side, n side. Okay, this is depletion region. Okay, there p side some negative ions and in hole n side some positive ions. Here in p side there is large number of hole and n side large number of electron, and we have connected with battery this. Okay, so now the positive side of battery, so inside the junction diode I have told the electric field due to immobile charge carrier. Okay, but is battery produce the electric field opposite to the this electric field. Okay, we know the battery produce electric field positive to negative. Due to this electric field, hole accelerate towards the n region and electron accelerated towards the n to p. Okay, when the applied electric field cancels the electric field inside here, means this applied electric field decrease the width of the depletion region, and when sufficient voltage given to the diode so that applied electric field compensate or cancel the inside electric field, or applied electric field when greater than the inside electric field, then we get current. Okay, that's why this biasing is called forward bias. Means when we connect positive terminal of battery to the p side and negative terminal of the battery to the n side, then we get current for sufficient applied voltage. Okay, for sufficient applied voltage means for very low voltage we cannot get, because low voltage cannot apply sufficient electric field to cancel the inside opposite electric field. That's why this is called forward bias. In case of reverse bias, we connected the negative terminal of battery with the p side and positive terminal of battery with the n side. Okay. Then here you can see that so the inside electric field and applied electric field in same direction, and which is opposite to the um, which are opposing the flow of hole and electron. That's why the width of the depletion region now increase. Okay, and we cannot get current. Also we get very small, means microampere range of current due to the minority carriers of electron in p side and hole in n side. Okay, this biasing is called reverse bias. So in reverse bias we get small amount of current. Okay. So now we will discuss diode characteristics, means IV graph. So I am plotting V along x-axis applied voltage and I along y-axis. Okay, and right side of x-axis is choosing forward bias and left side is reverse bias. Okay, so in reverse bias I have told reverse bias means positive terminal is connected to negative and negative. This is reverse bias. In forward bias I have connected diode by like this. Okay, so in forward bias first I am going to show the reverse bias. In reverse bias we get small amount of current, means we increase the voltage, we cannot get sufficient amount of current. Okay, we get only small amount of current, something microampere. Now if in forward bias I have told that for sufficient in voltage we get large current, means diode act as conductor. Okay, so if we apply small amount of voltage we get slightly higher current and becomes the current or like that. When sufficient voltage, applied voltage is sufficient, then we get like this current. Okay, and for silicon and this voltage, means below this voltage diode is not properly active, means not working properly, and above this voltage diode working properly. This voltage is known as knee voltage or knee point, knee voltage. Okay, or knee point. For silicon diode and knee point voltage is near about 0.7 volt. Okay, and reverse bias current is something microampere range, and forward bias current is very large. This is the diode characteristics graph. So, and diode resistance, you can see different point diode has different resistance. Here Vi difference. Okay. Here V versus I will be difference. Here V versus I will be difference. And for this value of V I is this. For this value of V I is this. For this value I is this. For this value of V I is this. Okay. So here the resistance is varying for different value of input voltage or applied voltage or for different current. So are the normal resistance, which is known as RDC resistance, is V by I, which is changing. Also like, and another resistance is called dynamic resistance, which denoted RAC also. Means if I choose a point here, we want to find the dynamic resistance, we need 2 points both side of this point at same difference and very small difference. Okay. Now there is a small voltage difference called del V. This is your del V, and there is a small current difference. This is del V, and this is called del I, and dynamic resistance is called del V by del I. This is called dynamic resistance. Okay, V by I. dynamic resistance. So in case of diode, we always calculate dynamic resistance rather than DC resistance. Okay. Now reverse breakdown and Zener diode. So we have seen that in diode the graph is, I am drawing again, in forward bias we get like this curve, and in reverse bias we get like this V versus I. Okay. But if we increase the sufficient reverse bias voltage, again at a particular voltage we get very large current. Okay. And this is called breakdown. And the voltage at which the diode becomes breaking, this voltage is called breakdown voltage and also known as Zener voltage according to the name of scientist Zener. This is called Zener voltage or breakdown voltage. Why this breakdown occurs, I will explain. So in case of diode, okay, there is two logic here. One is called Zener breakdown, another is called avalanche breakdown. Okay. So I have told this is P side and this is N side, and there is a depletion region. Okay. So in P side there is a whole number of holes, and in N side there is large number of electrons, and in P side some immobile ions for in depletion region. Okay. So if I connect negative in P side and positive in N side, but for sufficient very much high voltage, and for normal diode the breakdown voltage is very high, so we cannot get the breakdown. For to get breakdown, also we made a special type diode. By also there we increase the doping concentration. Okay, means the large number of hole here and very large number of electron here. That's due to increasing doping concentration, the width of depletion region decreases. Okay. And for low depletion, then if we for low depletion region, the electric field, reverse electric field is very high. We know electric field is V by L. Okay, so here voltage is applied voltage V, and L is the length, this length, width of the depletion region. So for heavy doping the length is very small, then electric field is very high, and for sufficient applied voltage the electric field is too much high that it can break the electron hole pair within the depletion region. And when the electron hole pair created by breaking a bond, then this hole now start going towards this, and electron now start going towards this, and we get a large amount of current. This phenomena is known as avalanche breakdown. Zener breakdown. You can see here, when reverse bias is increased, the electric field at the junction also increases. At some stage, the electric field becomes so high that it breaks the covalent bond, creating electrons hole pair. Thus, a large number of carriers are generated. This is called the large current flow. This mechanism is known as Zener breakdown. Okay. So for Zener diode, we need a very high doping concentration. Okay, we need very high doping concentration, so that the electric field produced very large. Okay. In case of avalanche breakdown, there is another logic that in P region there is small number of electron, and N region I have told there is small number of hole. These electron or hole, due to high electric field, they move with very high speed. When they are moving with very high speed, they collide with the covalent bonds and they break the covalent bond, and then new electron hole pair will occur, and this electron hole pair again accelerated by very high electric field, and they collide another electron hole pairs, and these electron hole pair they collide with another bond and produce electron hole pair. These electron hole pair again and collide with another bond, and this phenomena like chain reaction, a large number of electron and hole created. Okay. Then we get a large amount of breakdown, means reverse bias current. Okay. So you can see at high reverse voltage, due to high electric field, the minority charge carriers while crossing the junction acquires very high velocities. This by collision breaking down the covalent bond generating more carriers. A chain reaction is established, giving rise to high current. This mechanism is called avalanche breakdown. Okay. This Zener diode is a voltage regulator. One important application of Zener diode is voltage regulator. Here in Zener diode also, by changing the doping concentration and also the changing the semiconductor material, we can get the different breakdown voltages, and these voltages are very sharp. Okay, at particular voltage there will be a breakdown occur. Okay, we get also 3 volt, 5 volt, or 4.7 volt, 5.6 volt, 11 volt, like that breakdown Zener voltage, Zener diode. Okay, that means at this voltage the diode will break down and produce large amount of current, means act as conductor. Okay, above this voltage, and below this voltage it will act as insulator. Okay, in case of Zener diode voltage regulator, if here you can see the circuit diagram. So here input voltage applied, okay, and here resistance Rs is connected to series, and a Zener diode connecting reverse bias, and output, this is Rz or output voltage, or we can say RL, load resistance, and this is the output voltage, V out. Okay. So when V input is less than Vz, Vz is the Zener diode breakdown voltage, Vz. Okay, Zener breakdown voltage. Then Zener becomes now not activated, means no current is flowing through Zener, and so input voltage is only input. Due to the input source we get output current, and it is dependent on the RL and RS. Okay, we get output voltage variable. But if we applied voltage greater than Vz, input voltage is greater than Vz, now the Zener diode becomes activated. When the voltage difference between Zener is V input is very Vz, so that the Zeners become activated. Okay, means Vz now is constant. Okay, then output now we get only Vz. Okay. So if I input voltage vary, so above Vz must be, if I vary the input voltage above Vz or slightly, or depending on RS also, it depends on RS also, but so that this point voltage is always greater than Vz, or sufficient current produced by input, so that Zener becomes turn into breakdown. Okay, so at this condition the output voltage always Vz. We cannot get any other voltage when V input is sufficiently high. Okay, so that output voltage is independent on the fluctuation of input voltage, or very high for different high input voltages. Okay, so we can use Zener diode to get constant voltage when input voltage is varying. Okay, this is called voltage regulation. Okay. Rating of a Zener diode. Rating means all the instrument, electrical instrument or any instrument has a rating. Means suppose if you buy a bulb, there is rating is 220 volt, and so 220 volt 20 watt, or if you buy a LED tube light, 220 volt 20 watt. Okay, this is the rating. Okay, and also you can see in your home the fridge has rating 3 star, 4 star, 5 star. These are called rating. Okay, and also they have voltage, input voltage 220 volt, and 3-star rating means they acquire high wattage, and high star means 5-star means the device acquire low wattage. So rating of Zener diode is like VZ and power wattage, like that. So maybe 5 volt, 0.5 watt, like that. Okay, or 5 volt, uh, 1 watt, like that. Okay. So depending on rating and input voltage, we have to choose the RS voltage so that Zener will not burn. Okay. Suppose I am giving you an example. This Zener has voltage, suppose 5 volt 1 watt. So here we get output voltage, and I have chosen input voltage 12 volt. We have to calculate RS. When no current flowing through output, or there is no load condition, we have to calculate at no load condition. Okay, means output resistance infinite, there is no current flowing through output circuit. Okay, their resistance is very high or near about infinity. Okay, so the maximum current can go through or can survive the Zener diode. We have to calculate. We know Imax and Vz equals to power, and Vz here 5 volt I have told, Imax I have to calculate, and power here given 1 watt. Okay. That means Imax will be 1 by 5 ampere. Okay. So here 12 volt I have applied, RS I have to calculate. That means Imax I have got 1 by 5 ampere. So here input voltage 12 volt will be equals to the voltage across resistance Imax RS plus voltage across Zener diode. Now Zener diode in background condition, so voltage across Zener diode will be 5 volt. Then 12 minus 5 equal to Imax into RS. Then we can calculate RS. 12 minus 5 equals to 7 by Imax, means 7 by 1 by 5, 35 ohm. The minimum value, then RS, this is minimum value RS, we need 35 ohm. Okay. That way we have to calculate. Here is a problem. A Zener diode of voltage Vz equals to 6 volt is used to maintain a constant voltage across load resistance RL equals to 1000 ohm by using a series resistance RS 100 ohm. Okay. If EMF source is 9 volt, calculate the value of current through the series resistance. Series resistance, Zener diode, and load resistance. What is the power being dissipated in Zener diode? So just complete the circuit. This is RS, this is RL. Another is the symbol of Zener diode is slightly different than the normal diode. Its symbol is like this. Just first draw a normal diode and draw two line of the like this. Okay, this is the symbol of Zener diode. Here input voltage is 9 volt applied, Vz is 6 volt, and RL 1000, RL, this is RL is 1000 ohm, and RS is 100 ohm. Okay, calculate the value of current through the series resistance. Series resistance means RS. Current through RS we have to calculate. So first I have to check if if I disconnect the Zener, then voltage across RL. So when Zener connected, current will be 9 by 1000 plus 100 ampere, and 9 by 1100 ampere, and voltage across RL V, maybe VL will be I into RL. Okay, I means 9 by into RL 1000. Okay, you can calculate this near about 8 volt. Okay, that means greater than Zener voltage Vz 6 volt, which is 6 volt Zener voltage. So now if we connect the Zener, output voltage will be always 6 volt. Okay, so now we can calculate the current through RS. তাহলে IS current through RS will be 9 minus 6 by 100 means 3 by 100 ampere, 0.03 ampere. Okay, this is the IS. And RL, through the current through RL means IL will be VL by RL. VL means 6 volt. Current across, now Zener is connected, so voltage across RL always 6 volt. As Zener when not connected, the voltage across RL will be becomes 8 volt. So 6 by 1000 will be 0.006 ampere. Okay, so the current through series resistance we have calculated, current through load resistance we have calculated, and we have to calculate current through Zener. So IZ must be IS minus IL. Total current is IS, and current through RL IL, then this will be IS minus IL. Okay. Then IS minus IL will be 0.03 minus 0.006 ampere. You can calculate this. Okay, so that's all for today's class. Next day we will discuss more about the application of Zener diode, junction diode, and we will discuss also the photodiode, about photodiode and LED.